Now, some remarks concerning the orthocenter and the altitudes. Here, possibly, possibly the most interesting one, and well, perhaps not quite expected. Result is the following. So what we have got is the following: the triangle. Okay, and ABC, and we have dropped perpendiculars. Right, the altitudes, right angle, and right angle, and they intersect in H. Here it is. Now, I would like to ask you the following question, or invite you to think about it. So this is my A, this is my B, this is my C. So the orthocenter of the triangle ABC is H. Now, I invite you to think about the following question. Now, what happens if you don't take the triangle ABC, but let's say take the triangle HBC? So let me sort of shade this triangle in blue. Now, how are you going to construct the orthocenter of the triangle HBC? What was the orthocenter? Orthocenter is the point in which the three altitudes intersect. What are altitudes? Through every vertex, you drop a perpendicular to the opposite side. Vertices are H, B, C. From vertex H, you drop a perpendicular to the opposite side, and please observe that that altitude is in fact the altitude of the original triangle ABC through A. Good. And then, let's take the vertex B. If I drop a perpendicular onto the opposite side, which is CH, well, that altitude must be the side BA in the original triangle. And similarly, if I take in this triangle, in this blue triangle, the vertex C, and if I drop from that vertex to the opposite side a perpendicular, well, that must be exactly side CA. So what have I got? The altitude through H is HA, the altitude through B is BA, and the altitude through C is CA. So what's the orthocenter of, okay, so let me write this. The orthocenter of ABC, well, I know it, is H. The orthocenter of HBC is A. The orthocenter of H, well, right. Now, one of the nice things about the triangle is this, and you know, the way I'm choosing my notation in a cyclic fashion, etc., but notwithstanding that, the very nature of the triangle is democratic. So when you do something with one vertex, okay, unless you mention some very specific property of that vertex, okay, then it means that that property, that's reasoning, is also valid for the other vertices. So what I have done with the triangle HBC, and I have found that the orthocenter of the HBC is H, well, HBC is the vertex A. So you can similarly argue that if you take the triangle, let's say HAC, then the orthocenter of HCA is the vertex P. That's very easy to conclude. HCA. Observe the cyclic way of writing things. Well, I'm rather obsessed with that, but it's, as I say, very useful, ABC. Now, so it means that as long as you are dealing with altitudes and orthocenters, the 3 points A, B, C, well, they are only part of the picture. The whole picture is not ABC. The whole picture is A, B, C, and H. These 4 points. Why is that? Because you see, given these 4 points, take any 3 of them, remaining 4th is always the orthocenter of these first 3. The triangle which is which has its vertices at the 3 points. Okay? So these 4 points situated, so to speak, in exactly similar fashion. You see, now that's interesting. In the 19th century, people have used the word group in circumstances like that. Whenever you have got something in which one point is related to the rest in a certain way, and if you change the point, this relation will not change, okay? So that sort of thing has been referred to as a group. And so people have called this not ABC, the triangle ABC, but the 4 points ABCH as an orthic group. Orthic group. Okay, so these 4 points are entirely democratically related. There is no triple, or there is not one vertex among these 4 which is somehow more privileged. Okay, so they're all the same. Because pick one, and it's the orthocenter of the triangle constituted by the remaining 3. Okay, so nobody is privileged. So for that purpose, these 4 points are referred to as the orthic group. I mean, of course, this is just one way of looking at it, but in the future we shall see that certain properties and certain constructs attached to the triangle will turn out to be so-called orthic properties. Actually not related to just ABC, but related to A, B, C, and H in such a fashion as to make the 4 points, so to speak, a democratic union, right? Okay, so that's the term or orthic group, and this I would like you to consider as my first remark. My second remark is actually a very nice exercise in elementary geometry. I think this is something that you may really ask any bright preliminary school boy or girl, if you wish, nowadays. Yeah, it's the following thing. It's the following thing. There it is. Okay, so let me make this remark. Actually, why not? Why shouldn't I lump all my remarks together? So this is my remark 1. This is my remark 2. This is my remark 3. Now, well, let me formulate it directly. The reflections of the orthocenter okay, in the sides of a triangle lie on the circumcircle. Now that's a curiosity. Let me explain. Let me explain on the circumcircle. In fact, let me not only explain, but just start the thing. Let us, so to speak, think about the object. Well, it's always better to start with the circumcircle, because when you take the triangle, putting a circle through all 3 points is not easy. A, B, and C. Here's your triangle. Once again, let me observe the way I am at pains pointing out that the line joining 2 points is actually a line and not a line segment. So it's you know, paying attention to this sort of things is always rewarding. Well, wait and see. Okay, so that's your triangle. Now here is, okay, so what I'm trying to say is the following. If you take an altitude, let's take the altitude through A, okay? And that altitude will go through the orthocenter, of course, okay? And what I am saying is the following. The reflection of H in the side BC will be on the circumcircle. So this is going to be this point. So I don't know what you call it. Let's call it H prime A. So the cut. So what I'm trying to do is to show that. So so we have called the feet of the perpendiculars A tilde, B tilde, so on and so forth. So let me call this point A tilde. So what I'm trying to show is that this A tilde, okay, so this is a right angle. That's well known. So what I'm trying to show that is that this A tilde is in fact the midpoint of H prime. Equivalently, I'm trying to show that this thing, the length H A tilde is exactly the same as H prime A tilde. So that's what I'm trying to show. It's not too difficult to see. You see, if you look at this triangle C, okay, so that's H. So please notice that, okay, so the angle 1 and the angle 2. These are the angles. Okay, that's very bad. That's very badly drawn. Let me. I mean, of course, I can't make perfect pictures, but you know, I think I should at least strive to make some reasonable approximation. Okay, there it is. Okay, so the angle 1 and 2 are equal. Why? Because, well, they are simply the angles subtended by the arc BH prime in the points A and C. So I've got the angle 1 is equal to the angle 2. Well, that's not all. You see, if you observe that, well, quite simply, because this is a right angle, it means that A, okay, so I think I should call this also C tilde, okay? A, C tilde, A tilde, C, they lie on a circle. And in fact, a circle of radius AC, the diameter AC. So it means that 1 and 3 are also equal. You're finished. This is equal to 3. So 3 is equal to 2. And that's a right angle. So that means this is C, H prime A is an isosceles triangle. And in fact, the side CB is nothing but the perpendicular bisector of H tilde. Okay, so so BC is the perpendicular bisector of ne demiştik? H. Okay, so now that is going to be important, çocuklar. That's going to be important. So although it does not come into our computations or considerations or contemplations, let me point out that the center of this circle is of course O, right? The orthocenter and the circumcenter. This is a very interesting relation, and that constitutes my third remark. And this brings me to my fourth remark, which can be seen as a direct corollary. By the way, çocuklar, I mean, I'm not the kind of teacher who sort of likes to assign homeworks or something like that. But I strongly invite you to go home and draw my pictures again. And try to see what happens if you choose unusual triangles. By the way, does anybody use Geogebra? Is the name, okay, well, here's something. Geogebra. Well, this is, Geogebra is a free software. Okay, you can download it immediately. It's for geometric draftsmanship, so to speak. It's absolutely priceless. Okay, so what it can do is you take 2 points and you say draw a line, it draws a line. You take 3 points, okay, you say draw a circle through them, it draws. You take a point and you give a length, it draws a circle of that center and that length as its radius, and so on and so forth. And you can draw really beautiful things. Well, I don't know. You can also go to my Facebook page. There's a page in my Facebook account. There's an album called Geometry, and in which I've given some really very beautiful configurations, all drawn by Geogebra. So it's a very simple thing. It's great fun. It's great fun. I'm sure you will lose a lot of time on it, but it will be just fantastic. Okay, so Geogebra. Okay, so how about trying to draw this picture, starting with a triangle which is rather like this. Okay. So that's A, that's B, that's C. Well, this triangle was, of course, was an acute triangle. That means all angles were acute angles. So this is, for instance, this is an obtuse triangle in that B, the angle B, exceeds 90 degrees. It's more than 90 degrees. So it's I don't know, it's a thin kind of triangle, if you wish, or a fat kind of triangle, if you wish, whatever. So try to do the same thing with, you see, one complication will arise because you see the orthocenter of such a triangle will in the first place occur outside. Okay, so it will be somewhere here. So that's your B. So H will be here. Okay, and for instance, if you take the reflection of H in the side BC, it will be somewhere here. Okay. And I want you to go back to this and also study, for instance, what happens if you take, if you take the reflection of H in BC, I have obtained this. What happens if you take the reflection of H in CA? Well, it will get you something like this, won't it? So it's HB prime. And you can check that this piece and this piece are the same. You can do it with also the side B. So if you take the reflection of H in BA, you will get something like HC prime, and this piece will be the same as this piece. So first of all, check with all three. In a triangle, all vertices are democratically situated. Not one has a privilege over the other one. So if you do something with one vertex, you can do it with other vertices too. So bear that in mind. And of course, try the same thing with a triangle like this, and you will be rather surprised. You'll be rather surprised. For instance, look here, the reflection of H in CA. Well, it will be something rather like this. But you see, change the triangle as you might, this result will remain true, will retain its validity. But it's a very good exercise. And Geogebra does it automatically. Because you see, once you draw something, once you construct a configuration on the Geogebra, you can pick up a point and you can push it around. So your triangle will change and everything will change. You can actually see it happening before your very eyes. It's very instructive. Good. Okay, so that's my third remark, and that's a very good idea. It's a very good exercise in geometry. Keep an open mind. It helps you to keep an open mind. It helps you to think about possible alternatives. Okay, so my last remark is the following. So let me call it remark 4, lumping together all my remarks. It is the following. Right. So let me take a tentative diagram in this part of the world, and it is this ABC. That's the orthocenter. That's the point in which the three altitudes concur, and that is the orthocenter. The observation is quite simply that the angle between the altitude and one side, let's say C, that's the angle which I am designating 1, and the angle between the radius that joins the circumcenter to the vertex A with the side CA, which I am calling 2, shows that these two angles are equal. Now that's rather remarkable, and that's the kind of nice problem which you can ask a very young boy or a girl. And of course you can do it in many different ways. But the way I like to do it is to base it on this observation. Let me give you my favorite solution to this problem. Okay, here we are. That's A. That's my triangle. Okay. And I have a tendency, as you can see, I have a tendency to draw one side, according to our perception of gravity, in horizontal fashion. Well, this is a bad habit, actually. You should draw your triangles more freely. I mean, something like this, always. Okay, so, but I have this tendency to draw one side horizontal. It's a deplorable habit, but there it is. Okay, so, how do I go about doing this? So that's the center, O. And now let me base my reasoning upon this third remark. I drop a perpendicular. Okay. Yeah. And so this is the angle I'm interested in. Well, if you wish, this point is the point which I called HA prime in my last remark. So if I take the diameter through A, that means if I connect A and O, and if I extend it till it intersects the circle for a second time. Now, I have not been very good, so let me do some corrections, because I know what's going to happen. Okay. Right. So if I connect, okay, so let's call this point J if you wish. And if I connect J and HA, what do I know about this angle? Well, JA is a diameter, so that this angle must be a right angle. Are you with me? This angle is a right angle because it is the angle subtended by the diameter at any point on the circumference. That's the observation of Thalis, you remember, the simpler form of it. So this is 90 degrees. I know that this is 90 degrees. So it means that BC and HA, okay, so BC is parallel to HA, what I called HA prime, J. So what does this tell me? Well, it tells me that this arc and this arc are quite the same. Aren't they? So the angle that they subtend at any point on the circumference should be the same. So this is 1, this is your 2. There it is, finished. So this thing and do you get this? This is very simple. I mean, take a circle and draw 2 parallel lines. You see, these pieces will be the same. I mean, this will be the same as this will be the same as this. Okay? So that's rather obvious. Okay, so by the way, there are zillion ways of seeing this. Think about it, you will definitely find a solution quite peculiarly your own. Okay, so there's a problem with millions of solutions. This is just that I wish to sort of refer to this thing. Okay, they somehow belong together. Good. Now, okay, so I have presented you 2 remarkable points about the triangle. And by this time, I think you must have obtained a feeling for the word remarkable, the way I use the word remarkable. A point is remarkable with respect to a triangle if it is defined irrespective of a special property of a vertex. No, it is a property of the triangle as a whole. Okay, H is not the altitude of A and something. No, it is ABC. So it is something that is connected to the triangle completely. Okay, so, and well, I have promised 4. Let me go on to the 3rd remarkable point. The 3rd remarkable point is, in many respects, my favorite. Here it is. I'm sorry, I've got all this cleaning to be done. So let me keep this enumeration 1 and 2. But well, I think you have grown accustomed to my way of presenting remarkable points. Okay, here is your triangle. And let us look at the medians. Well, they are simply the lines that connect each vertex to the midpoint of the opposite side, so to speak. Okay, so Nadia, so what was our notation? The midpoint of BC was denoted by A prime. The midpoint of CA was denoted by B prime. And the midpoint of AB is denoted by C prime. Good. Now, it is a very simple thing, and I just wish to make it as if it drops out naturally. So the median, AA prime. So let me introduce the terminology. Medians. Median. Well, for instance, the line AA prime, BB prime, CC prime. This is an old subject. It has been studied so closely, and so many properties people have thought about, contemplated, and so many different quantities they have taken into consideration. And they have, of course, studied the lengths, AA prime. So if you take a median, Of course, it's what I mean by that is a straight line. It's an infinite object, of course. But if you look at the length if you look at the distance between A and A prime, that's a remarkable quantity. And it is usually referred to as the length of the median, and it's denoted by MA. So I'm not going to insult your intelligence by defining MB and MC, okay? But there are a few problems in the problem sheet about these quantities. It's very amusing. There are very amusing relations between these objects. Okay, and now let me get back. Okay, so let me take AA prime and BB prime, and they intersect in a point. Good. Well, what about it? Well, at this point, I have to behave like a conjurer. I have to draw something out of my sleeve because I want to make it as simple as possible. Let me draw a line which is parallel to BB prime through the point A prime, like this, okay? And it will, of course, intersect the side CA in some point T. Now, Theorem of Thalis about the proportions. You see, A prime divides the line segment BC in the proportion -1, okay? So opposite. So, well, it's the midpoint. Since A prime is the midpoint of BC, T must be the midpoint of CB prime. So these two are equal. So you must come to the conclusion that these two are equal. Well, that's good. But there is still another conclusion to be drawn from this. So if you call, for instance, this length 1, if this is length 1, if this is length 1 again, so what's this length? You see, this B prime is also the midpoint of CA. So if this is 1, this is 1, and so this must be 2. Are you with me? So yet again, let's apply the theorem of Thalis again. BB prime and A prime T are parallel. So if this is 1 to 2, so this must be some 1 prime, and this must be 2 prime. So it turns out that when you take two medians, when you take one AA prime, and if you let it be intersected by the other median, it turns out that the point of intersection lies on the line segment AA prime in such a way as to divide it into pieces in the proportion 1 to 2. Are you with me? Look, you take AA prime, and you have discovered that if you draw the other one, BB prime, then this must be 1 to 2. Okay, so that's picky. Well, here is an application. We say that a few moments ago I said, if you can do something with one vertex in a triangle, you can do it with the other. So, well, I have started with this median, and I have intersected it with the median through B, and I have found that the point of intersection must divide it in the ratio -1 to 2, opposite sides. Well, exactly the same thing must hold for the median that joins CC prime. So this median CC prime must also go through the same point. And that point, çocuklar, is called G. And it's denoted by G. And okay, so this G, it's called, okay, 3 medians. Concur in the point which is traditionally called G. So that this G comes from gravitation, because you see this point G is in fact the center of mass Well, if you assume your triangle is as a homogeneous quantity, so if the mass is distributed evenly and the gravity is homogeneous, then you can call it also the center of gravity. And of course, in those days, people did not know the difference between mass and weight anyway, so they called it center of mass and center of gravity. And G has stuck, and it's referred to as, and the name is centroid. And the really interesting thing, okay, so that's one thing. And the really interesting property is that the ratio of G A prime to, let me write it like this, G A is exactly the same as G B prime to GB. I will be publishing your problems tonight, and you will make use of this property repeatedly in some of the problems. The result is -1/2. Now that's rather, okay, so let me put that inside a frame to indicate that you are living through a historical moment. Okay, so that's the medians, and that's my third remarkable point. Okay, so we have got still the fourth remarkable point, and it will duly make its appearance. But before I do that, okay, so let me complete this picture. 3. Okay. Now here is something tragic. Here is something tragic. Here is something tragic. So if you wish, okay. You see, apparently these 3 points, the circumcenter, the orthocenter, and the centroid, these points have been known since antiquity in many different civilizations. It really doesn't matter which. Of course, most prominently Egyptian and Greek. Yet there was something interesting about these 3 points. And it's the following. So I would like you to observe, first of all, perhaps I should have mentioned this as a I had these remarks 1, 2, 3, 4. Perhaps this should be my remark 5. I mean, I should have perhaps mentioned this earlier, remark 5. I want you to observe the following. If you take a triangle, and if you take the midpoints as usual, okay? So as you can see, during the course of this lecture, I shall be drawing many triangles like this, and I shall be trying to make them as generic as possible. Good. So if I take the perpendicular bisector at A prime, and if I take the perpendicular bisector at B prime, they intersect, of course, in what we called O, the circumcenter. And if I join A prime and B prime, I know that A prime, B prime is parallel to, okay, so let me write. A prime, B prime is parallel to AB. Well, that's Theorem of Thalis. Now, I want to take the altitudes through A and the altitude through B, and they, of course, intersect in H. Now I want you to observe the following. OA prime, which is, of course, perpendicular to BC, and AH, which is, of course, perpendicular to BC, they are, okay, so OA prime is parallel to HA. So this side is parallel to this side. Good, but that's not all. If you look at OB prime, which is perpendicular to the side CA, well, compare it with HB, which is the altitude through B, and that means that's perpendicular to the side CA. So it means that BH is parallel to OB prime. So I've got HB. Now that's a remarkable thing because of the following. You see, you have obtained two triangles which are exactly the same. Again, this triangle, OB prime A prime, and the triangle HAB, they are exactly the same. The sides are parallel. A prime B prime is parallel to AB. HA is parallel to OA prime. HB is parallel to OB prime. So these two triangles have everything in common. They are similar. They are the same, except that the big one is twice the first one. Why is that? Well, if this is 1, then this is 2, isn't it? That's so simple. That's so simple. That's brilliant. So the triangles are similar. So I come to the conclusion that, now here is the remarkable thing. Observe that if you take OA prime, that is exactly half the length HA. I don't want to insult your intelligence by saying that similar things happen if you replace A prime with B prime. That would be an insult to your imagination and intelligence. Okay, so OC prime. Okay, so what is so great about this thing? Right. Enter Leonhard Euler. He is, in my opinion, without any argument at all, is just the greatest mathematician ever, Leonhard Euler, and he observes the following. I want you to notice the following tragic circumstance. The points O, circumcenter, H, the orthocenter, G, the centroid, have been known to humanity for thousands of years. Almost every civilization has got these points. These 3 points, whenever you get a triangle and you draw interesting things, these 3 points are there. But it takes Leonhard Euler to notice that. Okay, so Leonhard Euler. He notices that theorem. But this is not the whole story, but I shall mention just this theorem. The points G, H, O are in fact collinear. They lie on the same line, collinear, and the ratio of G, O to GH is exactly -1/2. Now why is that? Let me draw this picture again. That's AH. Okay? And let me draw this, OA prime. These are parallel lines. And what do I know? I know that this short line is half. So if this is 1, this is 2. So if I join O and H, and if I join A and A prime, what do I know about this point? I know that this point X, so, bakın. So it's not easy to draw a good picture. X must divide A prime A in the ratio 1 to 2. So this is 1 to 2, so this is 1 to 2. So this X, so the ratio of X, A prime to XA, must be the same, in fact, as XO to XH, and this must be -1/2. So this tells me AA prime is the median. AA prime is your kenar ortay. Okay, so and you are looking at the very point that divides it in the ratio -1 to 2. It is just the centroid. So this x is in fact G. But that's remarkable. That's remarkable. I'm not much of a historian, but it strikes me as a truly tragic circumstance that the points G, H, and O were known for many, I should say millennia, 1,000 years. The Greeks certainly know about them 2,500 years ago. Egyptians surely. And nobody noticed that these 3 points actually lie on a single line, and in fact, in a quite remarkable fashion. One dividing the other two, the line segment constituted by the remaining two, in a really rather simple proportion. That takes the genius of Euler. So this is one of the privileges of being a mathematician. As a mathematician, well, you may not be a genius yourself, but you are in a position to enjoy directly the product of genius.